Before I get started, I want to make sure I wish everybody a happy first contact day. As all Star Trek fans know, 39 years from today, the Vulcans will be landing in Bozeman, Montana, and so we've got that to look forward to. All right, let's talk about the universe. If the universe consisted of only two things, the sun and Mercury, then Mercury would just simply trace the same ellipse over and over and over again. In practice, however, that's not what happens. There are other things in the solar system besides the sun and Mercury. There's the gravitational effects of the other planets. And so the effect of those other planets is that it's not one simple ellipse, but it's more like a spiral, how the motion of Mercury goes around the sun. Now, and for what it's worth, similar nudges in the orbit of Uranus led to the discovery of Neptune in 1846. Now, the precession that you see on screen is greatly exaggerated by like a factor of 10 trillion. It turns out for Mercury, every 100 years, the orbit of Mercury precesses by 574 seconds of arc. If you remember, there are 60 minutes in a degree. There are 60 seconds in a minute. And so 574 seconds works out to be a little bit less than a sixth of a degree. So a very small amount over 100 years. Newton's laws of gravitation actually can be used to compute precession from the other planets, but the prediction was only 531 seconds of arc per century. That little itty-bitty difference, 43 seconds of arc per century, that's very tiny but measurable. This was first noticed in 1845, and for 70 years this was the great unsolved problem about Newton's laws. This small but measurable discrepancy between what is predicted and what's observed. And this wasn't resolved until 1915. Einstein's general theory of relativity pretty much exactly accounts for those 43 seconds of arc, which is what we're going to talk about today. And this was actually the first physical confirmation of general relativity. Oops, sorry about that. And by the way, 43 seconds per century is an insanely slow rate. I want to give you some idea of how slow that is. 43 seconds per century works out to be about a degree every 8,400 years, if you do the conversion, or a tenth of a degree every 840 years. All right, so let's talk about a tenth of a degree. Here I've got an ellipse. I'm going to start rotating this ellipse by a tenth of a degree per second. Every little nudge you see will be a tenth of a degree, and it's probably going to be easiest to see if you look at the 150 and 210 degree marks. Ready, set, go. Okay, so if you look at the 150 and the 210 marks, you can see each itty-bitty little nudge is about a tenth of a degree. If you look elsewhere at the ellipse, you can't see a thing, right? A tenth of a degree rotation, that's pretty much at the edge of human perception at this scale. Okay? And it's a tenth of a degree, not a second. It's a tenth of a degree every 840 years. Okay, so here we are in 2024. 840 years ago was Robin Hood. And Friar Tuck, and King Richard the Lionhearted, and King John. That's literally the era of Robin Hood 840 years ago. 840 years from now is another Disney classic, WALL-E. Okay? And of course, there's been a lot of things that have happened in the world in the last 840 years. And we got a lot of things to look forward to in the next 840 years. And in 8 centuries, the world becomes completely unrecognizable in 8 centuries. And the orbit of Mercury precesses by general relativity by that itty-bitty amount that I showed on the previous slide. So a very, very small amount. Okay, I should say at the outset that absolutely nothing in this talk is original. The source for this talk is this textbook that I took when I was a sophomore in college from an intermediate physics course. And so basically I've just taken the concepts in the book and just kind of try to make it presentable for a mathematical audience. So there's nothing here that isn't accessible at literally for an undergraduate physics major. This is something I took as a sophomore. All right, let me talk about some of the tools that we'll need in order to be able to do the talk. We'll need to know some ideas from precalculus. For polynomials, we need to remember how to complete the square and also how to find roots of polynomials. From trig, we'll need these principles from sine and cosine. Hopefully everybody has seen that. If you don't have it memorized, something that hopefully is recognizable. We'll need conversions from polar coordinates to rectangular coordinates and vice versa, that x is equal to r cosine theta, y is equal to r sine theta, r squared is equal to x squared plus y squared. These fact about two-dimensional vectors, or any vectors, that if the dot product of two vectors is equal to 0, if and only if the vectors are perpendicular. We'll need to remember what the equation of an ellipse is. So there's the equation of the ellipse, A squared, A represents the semi-major axis of the ellipse, B represents the semi-minor axis. The focus is located C steps to the left and right, where C squared is equal to A squared minus B squared. You'll notice that the focus, of course, is inside the ellipse, so C is less than A, and therefore the eccentricity C divided by A is going to be something that's less than 1. Okay, so some facts about ellipses we'll need. We'll also need some ideas from calculus. Okay, so the product rule. We'll also have the product rule for 3 functions. There's a version for the product rule for 3 functions, as well as a product rule for second derivatives. We'll need that. We'll need the ordinary chain rule. dy dx is equal to dy du times du dx. Cancel the du's. They're only fractions. It works out perfect. That's a joke. The derivatives on the right in red that everybody knows. The only one here from Cal 2 is that the derivative of e to the x is e to the x, but the others are from Cal 1. We'll also need these linearizations, the equations of tangent lines for sine of x, cosine of x, and 1 over 1 minus x if x is close to 0. And if you've taken Cal 2, you recognize this the first couple terms of Taylor series expansion. And we'll need Euler's equation, e to the I theta is equal to cosine theta plus I sine theta. We're also going to need a few ideas from physics, and so I want to spend some time making sure I talk about these. So in red is kind of the motion of the planet, if I don't know if it's an ellipse yet. And the displacement vector u is equal to r cosine theta I plus r sine theta j, where I is the unit vector going this way and j is the unit vector going this way. And you'll notice I'm using the mathematical convention, and physics is more like x hat and y hat to represent those vectors, but I'll just use I and j here. So I can factor out an r, and then what's left, the thing in parentheses, is a unit vector, u sub r, that points in the radial direction. So the green vector u sub r has length 1, just like the lengths of I and j over here, but it's pointing in the radial direction. Multiply that by little r, or by the non-bold r, and that gives me the displacement u. We also have the conservation of angular momentum, that the moment of inertia times the angular velocity is a constant. On the scale we're talking about, the planet is basically a point, and so the moment of inertia as it goes around the sun is mr squared, where r is the distance from the sun. So mr squared times d theta dt is some constant L. We also have the law of universal gravitation, that the gravitational force is proportional to the product of the 2 masses and inversely proportional to the distance squared. And the force, of course, points toward the sun, inwardly radially. And we have Newton's second law, force is equal to mass times acceleration. Okay, so I'm going to put all of those over here on my right. So the yellow box in the talk is basically my toolbox. Formulas that I have, which I'll need to use later. So I'm just going to put things that I'll need over here on the right for future reference. So that's it. We're going to need ideas from pre-cal, calculus, and these ideas from physics. This talk is purposely designed to be an elementary talk. If you haven't had this a whole lot, elementary in mathematics is a loaded word. In mathematics, in ordinary use, elementary means it's so easy a kid could do it. In mathematics, the word elementary tends to mean from first principles, as opposed to simple. And one of my favorite quotes about the word elementary comes from this book, 3 Pearls of Number Theory, that I took when I was a student. Here's the quote. All 3 problems have been solved by the most elementary arithmetical methods. Do not, however, confuse elementary with simple. As you will see, the solutions of all 3 problems are not very simple. And then 7 very, very long pages later, you see how complicated a completely elementary construction can be. In the next chapter, you'll encounter just as elementary construction, which is considerably more complicated. So this will be an elementary talk. All the steps will use steps from pre-calculus and calculus and a handful of physics that's on screen. It won't be easy. Every single step is accessible. What makes this talk interesting and challenging is that we're going to be using those ideas from pre-calculus and calculus in very creative ways. Okay, so a brief outline of the talk. Part 1, we will derive the differential equation for planetary motion under Newton's laws. Then we will solve that differential equation to show that planets go around the sun in ellipses according to Newton's laws. We will then tweak that differential equation and solve for the motion u, or the motion of the planet, if we have general relativity, and then from that solution we will obtain precession. So that's kind of the big outline of the talk. And so we'll start with the first part, deriving the governing differential equation. All right, well, one way to start is to start with Newton's second law. So force is equal to mass times acceleration. Acceleration is the second derivative of displacement. The vector u is equal to r times u sub r, that's in my toolbox. And so I can apply the product rule, the second derivative version of the product rule, to be able to write this out and expand out. That is correct. However, it's not going to be all that helpful. What we're going to do over the next few slides is take those derivatives in terms of time and get rid of time altogether, so that I can write r, the distance from the sun, as a function of the angle theta. Okay? So I'm going to reuse the chain rule to get rid of the t's and write all of those derivatives in terms of not derivatives with respect to time, but derivatives with respect to theta. All right, here we go. First derivative. dr dt by the chain rule is dr d theta times d theta dt. Cancel the d thetas. D theta dt is in my toolbox from the conservation of angular momentum. And so I can substitute. And now I will do something that looks completely out of left field. I will isolate the 1 over r squared and write that as the derivative of negative 1 over r. Now that is correct. The derivative of negative 1 over r is 1 over r squared. But this begs the question, why on earth would I want to do that? The reason I do that step is because if I take a look at those last two terms, I'm taking the derivative with respect to r times dr d theta, and by the chain rule again, I can combine those two to write that in terms of a derivative with respect to theta. And so the net effect is that I've written dr dt in terms of a not derivative with respect to time, but a derivative with respect to theta. Okay? All right, so second derivative. Second derivative, of course, is the derivative of the first derivative. And though, to quote the great philosopher, oops, I did it again. And we have to use again the chain rule to write that as dr prime d theta times d theta dt. Once again, d theta dt is in my toolbox, and so I substitute. And also the blue dr dt, I just got that on the previous slide, so I'll just substitute that in. The negative L over M, that's a constant, whatever it is. And constants can be pulled outside of derivatives, so I'll pull that minus L over M out. And then what's left is now a second derivative with respect to theta. And so I'm going to file that in my toolbox. The second derivative of r with respect to time is equal to this expression involving the second derivative with respect to theta. And now time has been taken out. Okay, so file that for future reference. We also need to take a look at these vectors that describe polar coordinates, how to describe the position of the planet in polar coordinates. So u sub r is equal to cosine theta I plus sine theta j. We had that before. That's the black vector u sub r, or r hat in physics convention. The purple vector u sub theta is equal to negative sine theta I plus cosine theta j. That also has length 1. And just as a quick check, if I take the dot product of those two things, you'll notice that the two terms cancel and I get 0, and so those are perpendicular. Okay, so those are my two vectors. Those vectors change as the planets move, unlike I and j. I and j stay fixed. But as the planet moves, the vector's u sub r changes, because u sub r always points away from the sun, and u sub theta is going to be perpendicular to that. So the vectors u sub r and u sub theta actually change as the planet goes around, and if something changes, that means it makes sense to take a derivative of it. So let's do that. U sub r, cosine theta I plus sine theta j. Take the derivative with respect to theta. Derivative of cosine is negative sine. Derivative of sine is cosine, and so there's the derivative of u sub r with respect to theta. Gosh, I've seen that somewhere before. And you'll notice that's exactly the same as what u sub theta worked out to be. And so we have that the derivative of the vector u sub r is exactly u sub theta, which I'm going to file in my toolbox. Okay, how about the other one? Take the derivative of u sub theta. Derivative of negative sine is negative cosine, derivative of cosine is negative sine, and so there's the derivative of u sub theta. That looks very close to the top line, except I have minus signs. And so this derivative is negative u sub r, which again I file for future reference. Okay. With all that, I am finally in position to write Newton's second law, not in terms of the rectangular coordinates I and j, but in terms of polar coordinates and the vectors u sub r and u sub theta. Here it goes. Force is equal to mass times acceleration. Acceleration is the derivative of velocity. Velocity is the derivative of the displacement. So for the moment, I'm going to forget about the top left and work only on the right. The derivative of displacement, u, that's r times u sub r, the distance times the unit vector. By the product rule, derivative of the first times the second plus the first times the derivative of the second. All right, now let me take a look at the red component there. That's a derivative with respect to time. So once again, by the chain rule, I'll write that as a derivative with respect to theta times d theta dt. Now the middle part, the derivative of u sub r with respect to theta, that's in my toolbox, and so I can substitute. And so I have now written the velocity not in terms of I and j, but in terms of u sub r and u sub theta. Okay, now I go back to the top line and substitute to figure out how the force vector is going to go. So up top, I've got the derivative with respect to time in black of this mess over there inside the parentheses. So the first part in red has 2 terms, the second part in blue has 3 terms. And so when I apply the product rule, I get 2 terms from when I take the derivative of the product of 2 things. And then on the second line, I get 3 things when I take the derivative of the product of 3 things. And let me emphasize parts of this. The part in red and the part in blue, I do the same chain rule trick to write this in terms of a derivative with respect to theta. So each of those I write as the derivative with respect to theta times d theta dt. Just using the chain rule over and over and over again. All right, let's bring that up top. Okay, let's take a look at the parts in color. The red du sub r d theta, that's over in the toolbox. The blue du theta d theta, that's over here. And the 2 terms in brown, they're just the same, so I can combine those. So the blue and the red I substitute from over here. The browns I'm going to combine, and so there's my simplification. And so now I have everything in terms of either u sub r or u sub theta. And then on my next step, I'm just going to put all the u sub r's together. So the reds are the u sub r terms, put those together. The blue and the green are the u sub theta terms, I put those together. The 2 blue terms are the same, and so I actually just combine those 2. And so, at long last, I come to the end of this calculation. That's F equals ma, but written in terms of polar coordinates as opposed to rectangular coordinates. All right, this force vector has to be the same thing as that force vector, right? F equals ma, and the only force that we're talking about here is gravity. So these 2 vectors have to be the same. For these vectors to be the same, that means the radial parts are the same, which means that the thing multiplying the u sub r's are the same. And so I'm now getting closer, very close, to the governing differential equation for the motion of a planet. Let's simplify this. You'll notice on the left-hand side, the second derivative of r with respect to time and the derivative of theta with respect to time, which are the last 2 things in my toolbox over here. And so I filed that away for future reference. Here's the future. So plug those in, and there is my governing differential equation, which I'm about to simplify. To simplify this, you notice there's an m common to both. So the little m's will cancel on the left and the right-hand sides. Also, the term in red I'm going to expand out on the next line, and so just simplifying, I get this. Now, you notice that I didn't write r cubed in the bottom. I wrote r squared times r. The reason I explicitly wrote it like that is because the left-hand side has a term in common, which I can then factor out on the next line. Okay, and then let's see. So again, comparing the left side and the right side. In red, there's a negative over r squared. Those cancel. The term in blue moves over to the right-hand side. And so I get, after all that work, this very short differential equation. And I'm going to make that even shorter. On the left-hand side, there's a 1 over r. I'm just going to, for the sake of simplicity, let me just call that u. Make it a whole lot easier to write. The constant on the right-hand side, and that's a constant. G's a constant, M's a constant, little m's a constant, L's a constant. I'm going to call that constant 1 over alpha. A very natural question, why did you call it C? Because it's a constant. More on that later. It turns out making it 1 over alpha makes sense later on. So again, I'm going to put up my toolbox and the things that I have over here. U is equal to 1 over R. That's a substitution I'll be doing over and over and over again throughout the talk. The 1 over alpha is a constant, and I don't feel like writing that mess out over and over again, so I'll just write 1 over alpha instead, and I can substitute in later. And so after all that work, I come up with this second order, constant coefficient, linear, non-homogeneous differential equation. For those of you that have taken differential equations, you can probably solve this in 3 minutes. The clock starts now. Everybody else, I'm assuming that nobody's taken differential equations for this talk. I'm assuming calculus. And so let's talk about how to solve this differential equation using the tools from calculus. It's a two-step process. So we're going to solve the differential equation and show that planets move about the sun in ellipses. Step 1. Let's make it a little bit simpler by just replacing the right-hand side by 0. Instead of having the 1 over alpha, let's make it a 0. That's actually a big simplification. I'll deal with the 1 over alpha in step 2. The technical word for this is a homogeneous differential equation, which is a fancy way of saying there's a 0 on the right-hand side. And so use of H means H for homogeneous. Okay, so let me rewrite that as the second derivative of the function is negative the function. All right. Can you think of some functions from Cal 2, plural, that when you differentiate them twice, you get the same function back, except you multiply by -1. Functions that when you differentiate them twice, you get the same function back, except with a minus sign in front. Any thoughts? I think I heard it. Yep.
Sine or cosine.
Sine and cosine. So sine of theta, cosine of theta. And it turns out that every answer is going to be a combination of those two things. A constant times sine theta plus a constant times cosine theta. That turns out to be the general form of the solution, which I put over here on the right in my toolbox. And so that's the answer for this homogeneous differential equation. I'm going to solve this a different way. That is the answer. In mathematics, if you can solve it one way, you haven't done it hard enough. There's probably more ways to solve it. And so we're going to solve this a different way. And this different way turns out to be useful later on in the talk. Let's suppose that something of the form e to the r theta is the answer. Where did that guess come from? You'll see why I made that guess here in about 10 seconds. Let's suppose that's the solution. All right, so that's u sub h. If I take two derivatives, well, there's the first derivative, an r comes down. Second derivative, another r comes down. And then if I add those bottom two lines in black, I get r squared e to the r theta plus e to the r theta equals 0. Because of the properties of the derivatives of e to the rx, the e to the r theta is in both terms, and so I can factor that out. And that product is supposed to be equal to 0. Now, even better, exponential of anything is never 0, and so that exponential term I can just simply cancel out from both sides. And so I get the equation r squared plus 1 equals 0. And the technical term for this is called the characteristic equation for the red differential equation on top. Basically, if I have that differential equation in red on top, the line on the bottom is a polynomial equation that goes with it. And if I ignore all the intermediate steps, I can kind of see how to write this down without the intermediate steps. The second derivative became an r squared. 1 times the original function became a 1 at the bottom, and that's it. Okay, so henceforth, I don't have to do the stuff in gray anymore. Okay, and I can write this characteristic equation directly from the equation on top. All right, r squared plus 1 equals 2. Quadratic equation has two solutions. What are they? R squared plus 1 equals 0, or r squared equals -1. That means r has to be equal to, it's Friday, r squared equals -1. What squared equals -1? I and negative I. So I have two solutions, plus I and negative I. Both of those, if I square them, I get -1. Now the whole point of this r was to plug into the purple thing over here. The r was my guess for what this thing looks like. And so this spits out two solutions, e to the I theta and e to the negative I theta. From Euler's formula, e to the I theta is cosine theta plus I sine theta. E to the negative I theta is the same thing, cosine of negative theta plus I sine of negative theta. All right, from here we use some of our properties of trig functions. Cosine is even, sine is odd, and so I use that to get rid of the negative for the cosine. For sine, the minus sign pops out. Then I'll combine the cosines together and then rename the constant, and I get C1 cosine theta plus C2 sine theta, which is what I had in the first place. And so after all that work, I've come up with a second way, equivalent as it turns out, of being able to solve this homogeneous differential equation. So, step one, replace the 1 over alpha by 0 and find a solution. There it is. Okay, step two, let's now deal with the 1 over alpha. We're now going to guess at a solution for this. I'm going to guess at one solution for this, and when I put up the guess, hopefully you'll see why it works. The guess is going to be, let u equal 1 over alpha. Let u just be a constant function. Boring. No matter what you plug in for theta, you get 1 over alpha. The reason this works is because 1 over alpha is a constant. When you take the derivative of a constant, you get 0. Second derivative of a constant is 0. And so when I add the brown and the purple lines together, I get 1 over alpha, which is exactly what I wanted to have in the first place. Okay? So that checks that that is a solution. Okay. So to this point, we've got the solutions to the homogeneous equation. We've got a solution to this non-homogeneous equation. And the technique from here to be able to find all solutions of the equation in black in the top left is to simply just add the two things together. Okay? Now, I need to justify why this works, but this does work. Let me justify why this works. So there's my guess that I'm going to try. Well, let's see if it works. There's the first derivative. The derivative of a constant is 0, but otherwise just take the derivative. There's the second derivative. And now if I add the line in blue and the line in red up, then I see that the cosines cancel and the sines cancel. And then all that's going to be left is 1 over alpha in black, which is exactly what I wanted to have in the first place. Okay? So after all that work, top left gives me what Newton's law says the motion of the planet is. Top right, that's my solution of the differential equation. And for those of you that have taken differential equations, the 3 minutes is up. Okay? So that's the solution of the differential equation. All right, from Cal 1, when you have the constants C1 and C2, when those pop up when doing integral problems, we have to have some kind of initial condition to solve for those constants. Here's the initial condition that I will choose. We suppose that the planet is closest to the sun when theta is equal to 0. The planet's going to be closest to the sun someplace, and wherever that is, I'm going to define that angle to be theta is equal to 0. All right, so that spits out one initial condition right away. U of 0 is 1 over r, and r of 0 is how far the planet is from the sun at its closest point. The technical word for that is perihelion, for closest to the sun. So 1 over p for perihelion, that's whatever the distance is from the sun at its closest point. The second initial condition I will use from the word closest. Closest means that r is minimized. If r is minimized, if I take the reciprocal u is maximized. And whether that word is minimized or maximized, there's something that special happens to a derivative when a function hits a local min or a local max. At a local min or a local max, the derivative is 0. And so that brings me to the second initial condition, that u prime of 0 is equal to 0. Okay, so those are my two initial conditions. I'm going to deal with the second one first. My original function in u is on top. There's the derivative. I now plug in 0. When I plug in 0, sine of 0 is 0. That goes away. Cosine of 0 is 1. And so all that's left is C2. So from the two lines in red, I conclude that C2 is equal to 0. I take C2 equals 0, plug in way up top, and that sine theta on top nicely just goes away. We like that. Okay, now for the other initial condition. I know that u of 0 is supposed to be equal to 1 over p, whatever p happens to be. Okay, and so cosine of 0 is 1, and so just get C1 all by itself. And there's my formula for the other initial condition, just isolating the C1 all by itself. And so take that and plug into this red C1 on top, and there is my solution for u, which I will now rewrite. Okay, let's get a common denominator for u. The reciprocal of u is r. And now I will simplify this in a way that doesn't look like I'm going to simplify it, which is multiply top and bottom by 1 over p. If I multiply top and bottom by 1 over p, that blue p becomes a 1. The red alpha times p becomes an alpha, and the purple mess becomes a bigger purple mess. Okay? And again, to save myself some writing, let me call that purple mess just epsilon. Okay? And so I'll file both of those in my toolbox. And so there's the motion of a planet under Newton's laws. R is equal to alpha over 1 plus epsilon cosine theta. And where epsilon is this messy fraction over here. Quick aside, I'm going to need this later. If I take the reciprocal of that, that's going to be u. Then if I plug in u equals 0, cosine of 0 is 1, and I just get 1 plus epsilon times alpha. Just a quick aside, I'm going to need that later. So that turns out to be an ellipse, which I'm about to demonstrate. That is the polar form of an ellipse. All right, now, you don't just take my word for it, let's do it. To show that it's an ellipse, we multiply up, then distribute the r. You'll notice the r cosine theta. R cosine theta is equal to x, and I have successfully gotten rid of all the thetas. Now, to get rid of the r, let's get the r all by itself. Square both sides. R squared is equal to x squared plus y squared. And now I have gotten rid of all the r's and thetas and have traded them for x's and y's. Okay? So I've successfully converted from polar coordinates to rectangular coordinates. To show that this is an ellipse, to show the common technique, we leave the constant on one side. The only constant here is alpha squared. And everything that has an x or a y in it, we move over to the left-hand side. Okay, so let me bring that up. The first two terms have an x in them. The third term on the left does not. So the two terms on the left, let me factor out 1 minus epsilon squared. So I have just 1x squared inside the parentheses. And I have a big gaping hole inside the parentheses, which I'm emotionally blackmailing you into thinking my next step is going to be completing the square. To complete the square, I need to take the part in red, the x coefficient divided by 2, and square it, and then add that inside the parentheses. And then I have to add something on the right-hand side to compensate. So the thing in parentheses is now a perfect square. And then on the right-hand side, I just simplify to get this. Okay, and then finally, to show that's an ellipse, on the right-hand side, I'm supposed to have 1. Remember the form for an ellipse. So to get a 1 on the right-hand side, I'm just going to divide by the thing on the right-hand side, and I get this big mess. It's a mess, but it does match the form of an ellipse. And I've kind of color-coded the parts that match. I can see h and k, that's going to be the center of the ellipse. A squared is going to be the thing in green down here. B squared is the thing in purple down here. And so after all that works, I've shown that the motion of a planet is indeed an ellipse. Now I'm assuming that epsilon is less than 1. If it's greater than 1, it turns out to be a hyperbola. But for a stable orbit, it's going to be an ellipse. A few things about this ellipse. Let me first take a look at the part in green. If I take the square root over there, a is equal to alpha over 1 minus epsilon squared. And I can rewrite that as alpha is equal to a times 1 minus epsilon squared. And so I've written alpha is basically proportional to the size of the ellipse, or miraculously the semi-major axis of the ellipse. Okay, focus of the ellipse. The focus is found by c squared is equal to a squared minus b squared. So there's a squared, there's b squared. Then if I just do the algebra, get a common denominator and simplify, there's c squared. Okay, now if I take the square root of both sides, that shows me that c is equal to alpha times epsilon over 1 minus epsilon squared. Gosh, I've seen that somewhere before. That exactly matches what I see over here. And so the center of the ellipse is located at negative c, 0. And then if I take c steps to the right, I get to the focus. Look at what else is over here. The sun. And so that demonstrates that not only does the planet move in an ellipse, but that the sun is at a focus of the ellipse. One last thing. The eccentricity of the ellipse, c divided by a. So if I take the red divided by the green, that's a mess, but you notice that most of the top and the bottom actually cancel out. And all that's left is the epsilon in black. And so that demonstrates that the eccentricity of the ellipse is that number epsilon. And so I don't have to remember the formula for epsilon anymore. The eccentricity of the ellipse is directly measurable by telescopes. And so that's just the eccentricity of the ellipse. So, catching our breath. Newtonian physics. There's my governing differential equation. Here's the solution under Newtonian mechanics. If I take the reciprocal, that's the motion of the planet, and I've just shown that that's an ellipse. All right, we are now going to tweak this differential equation for general relativity. And here's the tweak. I'm going to add a second term on the right-hand side. Plus g times m divided by c squared over u times u squared. I'll say at the outset, the natural question is, why is it that? The answer is, honestly, I have no idea. I've tried to figure out how to go from general relativity, step, where that thing comes out. I failed miserably. If anybody has a good reference, I'll be happy to read it. But for now, we'll just run with it, that was the formula that was in my sophomore physics textbook, and so we'll just run with that as the right-hand side. I should also point out about the c squared at the bottom. I hate when speakers do this, but I'm about to do it. A slide ago, c was the focus of the ellipse. From now on, c means the speed of light. Okay? So, unfortunately, this has been like a great argument between mathematicians and physicists for centuries about the proper meaning of c squared. So, physicists think one thing, mathematicians think another thing. I'm not going to try to resolve this debate. I'll just simply say from now on, c means the speed of light. Okay, so we're now going to solve this tweaked differential equation to find the motion of planets under general relativity. That fraction, let me call it delta, just because I don't want to keep writing that fraction over and over again. And so this is now a proper math talk that it has both a delta and an epsilon in it. And delta, you want to think, is a small number. I'm dividing by the speed of light squared. That's a very, very small number, so that's a very small perturbation to Newton's second law, or to what we found in Newtonian physics. All right, what do you do if you're taking differential equations and your professor says, solve this nonlinear differential equation that's second order? The answer is you throw rocks at the professor. This is really, really hard. And so I'm not going to solve this exactly. What I will do instead is to make an approximate solution. And the approximate solution is, where I see u of theta on the right, let me substitute the solution that I had before. Okay? The idea is, that's not exactly right on the right side, but it's close, really close. And so, to solve for u on the left-hand side, I'll make this substitution on the right-hand side, and therefore get a better approximation to the motion of the planet. Okay, so this is called actually the method of successive approximations is the technical name for this. So we'll solve this. Square out the thing in brackets, and then you'll notice there's a cosine squared over here on the last term. I've got a trig identity for that to get rid of the square to write in terms of cosine 2 theta. And then the last term over here in parentheses, we'll just expand that out. And so I've got this 5-term thing now on the right-hand side. The 1 over alpha is what I had before. The 4 terms that follow are new. And you notice that the first 3 terms in red are constants. The term in purple is cosine theta times a constant. And the brown is cosine of 2 theta times a constant. So I will solve this in 3 steps using those 3 parts. Step 1 is by far the easiest. Okay, so ignore the terms in gray at the moment and just look at only the constant. Morphologically, this is exactly what I had before. Second derivative plus the original function equals a constant. And I know how to solve this from my previous work. It's going to be C1 cosine theta plus C2 sine theta plus this extra thing. The extra thing is the same constant that you see on the right-hand side. So just by similar work from what we had before, I've got these things. Let me expand my toolbox to the bottom and store those for future reference. Okay, second derivative plus the function is equal to just the thing in red, and I'll ignore the stuff in gray in the middle for the moment. All right, if you've taken differential equations, you know the method of undetermined coefficients, which can be used to solve this. Again, I'm not assuming differential equations. What I'm going to do is solve this using only calculus, and by the way, I'll be showing why the method of undetermined coefficients actually works. So that's a little detail we often skip in differential equations. Here's the technique, but we often don't say why the technique actually works. I'll show you how to do this. All right, here's the trick. I'm going to write the top line as the thing on the right. Second derivative plus the function is equal to capital Y, where capital Y is equal to the function on the right. For the moment, I'm going to forget about the one on the right, and I'll just deal with the thing on the left, and I'm going to find a new differential equation for which capital Y is a solution. In other words, I'm going to play Jeopardy. Capital Y is the answer, and I'm going to find the question, the differential equation that goes with it. Okay? To do so, there's the derivative of capital Y. There's the second derivative of capital Y. And you'll notice that the second derivative of capital Y looks very much like Y. The parts in blue match. So the second derivative of capital Y is equal to negative 4 times Y. Bring that over to the left-hand side, and I've got the second derivative is plus 4y equals 0. And that's going to be a differential equation that capital Y solves. All right, the next thing that I do, everywhere I see a capital Y on the left in red, I will substitute the thing over here on the right. And so I make the substitution. So everywhere I see a capital Y, I'm going to make the substitution that I see over here on the right. And then let me expand this out. The second derivative of a second derivative is the fourth derivative. In brown, I've got 5 times the second derivative, and then lastly, I've got 4 times the original function. And so what I have done is that I have traded the original differential equation on top, which was second order, for something that is now fourth order. And you think to yourself, great, how's that help? The reason this helps is because the right-hand side is now 0. And because the right-hand side is 0, I can now use the characteristic equation that I saw before. The fourth derivative becomes an r to the fourth. 5 times the second derivative becomes a 5r squared. 4 times the original function becomes a 4, and that is the characteristic equation that's associated with this fourth order differential equation. And this now becomes an algebra 2 problem. All right, that factors quite nicely, actually. And so r squared is equal to negative 1, or r squared is equal to negative 4, and I get 4 answers. Plus I, negative I, 2i, negative 2i. And then from those 4 answers, using Euler's formula like I did before, I actually get these 4 solutions. Cosine theta and sine theta, just like I had before. And the other 2, cosine 2 theta and sine 2 theta, those come out just like before, and there are 2's here because there happens to be a 2 right here. And so there is my solution for that differential equation on top. Now I need to solve for C3 and C4. To solve for C3 and C4, there's the second derivative of u sub 2, and I need to add those 2 lines together. Okay, the whole point was to add the second derivative plus the original function. When I add those lines together, the reds cancel, the blues cancel, the browns combine, and the purples combine, and so I get negative C3 cosine 2 theta minus 3c4 sine 2 theta, just adding those two lines up and canceling, combining. And that is supposed to be equal to the original right-hand side. I can now match parts. The red cosine terms have to match, and the blue sine terms also have to match. I can see right away C4 has got to be equal to 0 for those to match. To get C3, I'll take this and divide by -3. And so I can get that C3 is equal to this fraction, which I get when divided by -3. C4 is equal to 0. And so when I plug those in for C3 and C4, the sine term goes away. And I recognize at least two of those three terms. The first two terms are my friends, C1 cosine theta plus C2 sine theta. I've been seeing that for the last half hour. The thing that's new is the term in red. And so that is my second particular solution for the right-hand side. And so I'm going to file that for future reference. Okay, 2 down, 1 to go. The one that's left is the term now in red, the one involving cosine theta. And I apply pretty much the exact same technique. Okay, so we just let capital Y be equal to that right-hand side. And then I notice that the second derivative of capital Y, when I take two derivatives, derivative of cosine is negative cosine. Second derivative of cosine is negative cosine. So that's equal to negative the original function. And so that means the second derivative of y plus y is equal to 0. Again, I apply the exact same technique that I had before. Everywhere I see a y, I replace by the thing on the right-hand side. And so I get this characteristic equation. Now, r to the fourth plus 2r squared plus 1 is equal to 0. All right, that's a perfect square. And so I get 4 roots, but there's actually only 2 answers, plus I and negative I. So from those 2 roots, it looks like I only have 2 answers. I've got C1 cosine theta and C2 sine theta. And I'm missing 2 of them. To find those missing 2 solutions, there's actually a technique for this. And the technique is simply to guess at an answer. And we'll guess that something times cosine theta works. The idea is that I know that a constant times cosine theta works. Maybe something else times cosine theta works. Let's press our luck and see what happens. And so to see if this actually works, I've got the little detail of plugging into the left-hand side, which means finding the second derivative and the fourth derivative of the thing in red. So if you're real careful, there's the second derivative, just applying the product rule real careful. Apply the product rule even more carefully to get the fourth derivative. And then I plug those in over there on the upper left, and I get a big, ugly, hideous mess. That's a technical term for it. Okay? It's a big. If I change the colors, it's not quite so bad. All the reds cancel. Over here on the right, all the browns cancel. The blues over here combine. And so, yeah, it's a mess, but not as bad as the mess as I had in the first place. And the goal is to make this equal to 0. Well, I can make this equal to 0 if all of those color terms are 0. If all the things in color are 0, then it works. We're going to get 0. And it turns out it's 3 for the price of 1. I can make all of those 0 if the second derivative is 0. If the second derivative is 0, that means the third is 0. And that means if I take another derivative, the fourth derivative is 0. So 3 for the price of 1. All those are 0 as long as the second derivative is 0. Okay, and so that means the first derivative must be a constant starting to green, which means that the original function is linear. So after all that work, the g of theta guess that I had is going to be something that is linear. And I can expand out. You notice 2 parts. C1 cosine theta. That's my friend that I've seen over and over again on the bottom left. The thing that's new is the theta times cosine theta. That's a brand new solution. And by the exact same logic, theta times sine theta also works. If you take differential equations, you know that if you have double roots for the roots of the characteristic equation, you multiply by theta. That's pretty much the calculation that justifies y. So from the 2 on the bottom plus these 2 new ones, there's my general solution for this 4th order differential equation. Once again, I must solve for C3 and for C4, which means finding the second derivative and add.
So second derivative, there it is. Now I have to add the two together. That looks like a mess, except the reds cancel, the blues cancel. Over here, the browns cancel, the purples cancel. So all that's going to be left are the two terms in black. And that's got to be equal to the original right-hand side. So matching up the pieces, you see that C3 is going to be equal to 0, and I get C4 by dividing by 2. So I plug those down here at the bottom, and there is my third term in blue. The red is my friend that I've seen over and over again. The term in blue is what's new, which I found right here. So finally at the end, in purple, I got this term. In brown, I got this one. Blue in the fourth term, I got this one. And the rule is to find the general solution of the original thing, I just add everything up down here at the bottom. And that's going to be the general solution of that differential equation. All right, now the constants, C1 and C2. If I plug in 0 on the right-hand side, the things in black go away. The things in brown is a constant. Cosine of 0 is 1. And so I get an equation for the blue C sub 1. So just get the C sub 1 by itself. And so step, 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 you get the C sub 1 by itself. Okay, so there's C sub 1. To get C sub 2, we take the derivative of both sides. When I plug in theta equals 0, almost everything on the right-hand side goes away. Because sine of 0 is 0, and also in green, 0 times anything is 0. So when I plug in 0, the only thing that's left is the blue C2, which is therefore equal to 0. So plugging the two formulas here in the bottom, the blue C2 goes away, and I just get this. Now let me rearrange this slightly. The things in red I'm going to combine, so I'm going to multiply out that bracket and put the red things together. I get 1 plus epsilon cosine theta over alpha, then all these other terms that are next. And that is the solution of the motion of a planet under general relativity. You'll notice that the leading term is what I had before from Newton's laws. That's Newton's laws. Everything else is a perturbation from the ellipse that I'm expecting. All right, with the time I got left, we're going to get precession.
Similar.
Which of those 5 terms is most important? As theta gets big and the planet keeps revolving around the sun, which of those is most important? Well, the browns are constants. The purple terms are bounded because cosine is between -1 and 1. The only term that grows is this last one. And so I get that the last term is the only thing that's important. So the gray terms, I'm just going to get rid of. The last term is what's most important. All right, let's simplify this. Put everything over alpha. Now the second and third terms have an epsilon red in common, and so I'll factor that out. And now I will do something completely out of left field and use the approximation sine of x is approximately equal to x, if x is small. That red thing is certainly small. Delta is small. Alpha is proportional to the distance of the planet from the sun. That's big. That red thing is very small, and so I'm allowed to make the substitution using kind of Taylor series in reverse, that the red thing is approximately sine of delta times theta over alpha. Now, for the blue one, I know the cosine of a small number is approximately equal to 1, so I'll just replace that by the cosine of the same thing. Now, why in the world would I want to do that? The reason I do that is now I've rigged things. Cosine of the first, cosine of the second, plus sine of the first, sine of the second. Bring back any bad memories. That's equal to the cosine of the difference of the first minus the second.
What's the advantage of it?
Okay, now I see there's a theta that's common to both, so I'll factor that out. And u is 1 over r, so if I take the reciprocal, I get the distance from the sun.
Right.
And that is the equation of a spiral. If you plot that in Desmos, that's the equation of a spiral. Okay? You'll notice that if I ignore this, that's the same thing as the term in red. If I ignore this is the thing that causes the precession. And let's kind of take a close look at this. So here's perihelion at theta equals 0. The planet goes around the sun once, and then its next closest point is no longer straight to the right, but somewhere to the northeast. And that extra amount of rotation, the amount above and beyond 2 pi, that is the precession. Okay, so the goal is to figure out how the value of the sun, the value of theta, the next time it's close to the sun. All right, if I want r to be as small as possible, as close to the sun as possible, then I want the denominator to be as big as possible, which means I want cosine to be as big as possible. To make cosine as big as possible, then that angle in red better be
2.
If I want cosine as big as possible, the angle better be a multiple of 2 pi. Okay, and so the next time it's going to be close to the sun, I want that angle to be equal to 2 pi and solve for theta, which is therefore the easiest part of this entire presentation, solving for theta. Theta is going to be equal to 2 pi over the thing in brackets. And then using the geometric series expansion, that's approximately equal to 2 pi times 1 plus delta over alpha, or 2 pi plus something, and that something is the precession. That something is the precession, the number of radians per orbit that the orbit spirals. Now, finally, in my toolbox, delta now for the last 2 things left. So I'll just plug those in. And then the toolbox goes away. Multiply out, and there is my formula for the precession of a planet's orbit. After all that work. Now, after all that work, it better work. Okay, Mercury.
Yeah.
There are the numbers for Mercury. The gravitational constant of the universe, the mass of the sun, the length of the semi-major axis, the speed of light, and the eccentricity. We plug in, and we get 5.032 times 10 to the minus 7 of this hideous unit. Just looking at all this stuff in color up there above. So that is a hideous unit, and the good news is that everything cancels. And the units are really radians per orbit. It's dimensionless as far as I care about meters and kilograms and seconds. So, 1/2 millionth of a radian per orbit. Let's turn that into centuries. The length of Mercury's orbit is at 0.2408 years, or 0.00248 centuries. So if I convert radians to degrees to seconds, and then orbits into centuries, that becomes 43.1 seconds per century, which is pretty much what we observe telescopically. Okay. We can do the same thing for another planet, Venus. Just do the exact same calculation. And we get that it's 8.65 seconds per century. And that again matches what we see in our telescopes. Just kind of an historical footnote, that was unobserved by Einstein himself. With the telescopes that are available in 1915, the precession of Venus was not observable when the General Relativity was published. It wasn't observable until 2 generations later. Unfortunately, Einstein had died by then, but he had plenty of other things that pat him on the back before he died. So I'll close this talk with this nice picture of Mercury. In the upper left, the formula for precession, and the quote that I gave you at the start of the talk. You see how complicated an entirely elementary construction can be. Thank you very much.